Yeah, but you know it's more than symbolic because of the synchronization aspect.
Okay, wait. So then, are we doing it again right now?
Not yet. Let me fire up my Mac first because that way we can.
I apologize. I'm probably loud.
Yes, whatever it was that. Let's do it. Samples.
The faces not
The base?
The spider.
Oh, the spider's still there because someone left the water bottle. I have a basket. That's all I know. Okay, we're good here. Trust issues with this camera. Oh, I could have just asked you. Yeah, it is recording. Okay, just making sure.
Is it just the blinking that means it's recording?
Yes, and blinking red, and if you look at the thing over here.
Oh, and there's people.
All right, as usual, Ray, I'm short this fast because the person who's here is Don't worry. Okay, thanks you guys for the passing stuff.
Can you give
Okay, thank you.
two to the back?
We'll actually leave this around here for collection.
Oh, look, one more.
Oh, yeah. Today we are going to have, anyone have AAA batteries on them by any chance? I need 4 AAA batteries. Because I've got, okay, DY. Ah! Okay, or, the question is what order? But I need 2 more. Guess what? For what? Oh, no, but you want to sacrifice your calculator? Yeah, who needs calculator? I want to tell Ken Ali. Okay. Here. You guys do DU, DV. Okay. All right. Why is it so silent, everyone? You guys okay?
Because we're waiting to listen to you. There's so much to say.
Why do you want to listen to me?
Wait, can you like do the, you said.
Oh yeah. Oh, that's okay. So we're all saying so for clapping.
Oh, yes.
Right.
Wait.
All right. So 1, 2, 3. And the audio waveform will be up. Hello. Oh, nice.
Wait, so can I be DB?
Yeah. Well, DU, DV are actually going to be used to.
Oh.
But you can be DY. You can be DX. Yeah.
Oh, it's hold it.
Press and hold.
Yes.
Okay, we got it. Okay. All right. I created a monster. Okay. Today we are going to talk about polar coordinates. We'll do a couple of clarifications about double integration because procedurally there was one bit that I missed. So I just want to say in general, if we have this, so we have double integral d. What do you want to do? What order do you want to do? Okay. Okay. dy dx it is. Okay. And we have integral of f of x y dy dx. And then we have these bounds here. And then we have these bounds here. This is not a symbol. This is arbitrary. This is called squiggled. Okay. The thing that I want to drive home is how do you solve a double integral? The key is to know that, like inception, it is a thing inside of a thing. It is an integral inside of an integral. So the way you do it is you look at this, and you say, hey, this is my inner integral. And you solve your inner equals integral from blob to blob of f of xy, of f of xy. My mouth isn't working. F of xy, dy, okay. That makes sense.
Yes.
And then the outer, the outer is going to be the integral over its respective bounds of what?
Yes.
Over dx?
Sorry.
Of what? What goes in here?
The actual integral.
Well, no, but so we're going to do this integral and we're going to get a value.
The value of the inner?
Exactly, so it's the integral of inner. So if this gives you, 5x squared plus 3, what goes in here? 5x squared plus 3. Does that make sense? Okay. Okay, that's a big point of clarification. Are there any other questions that you have about the double integration as you have started the PSET? WTF is a valid question.
It's kind of weird that he didn't.
Was this caused by double integration?
Oh.
Blow of double integration to the head? You okay?
Is there a reason why
This
they're
is what's possible.
technically energized?
But it's just
Like they're
reciprocation,
separate
I don't
things,
know.
right? What does that look like graphically?
What is that like graphic? That's a great
It's
question.
like you're holding one part, but then you're ignoring the
If I
other.
go to
Yeah, that's exactly it. So remember, let's do our general region that we're finding the integral of over here. So from A to B, what is a good order of integration
schedule is
here
crispy.
if we're going to find the area? What was that? Aha, so we're going to do dy.
Try.
Uh-huh.
Yes.
All right, I get with it, you guys. Okay. So the integral, and if we're going to find the area of this, what's our integrand?
That, yeah, you're
Oh.
Take too much time.
1. If we're going to find our area, our integrand is 1. Or just don't show it.
I just take.
Remember that what we're doing is we're finding the areas of these little rectangles and we're summing them together. So what I'm saying is that the height of that rectangle is the easiest one to capture first. And the height of that rectangle is going to go from here
Oh, that is.
to here. So our bounds are going to be, what do you want to call this function? Y equals 3x and y equals, I don't know, x cubed minus 2x plus 7 or something, some random function. And I know that my bounds are going to be this, 3x to x cubed minus 2x plus 7. Inside, I'm handling the dependence between y and x in such a way that by the time I'm through, and I've done integrating with respect to y, once I integrate with respect to x, I use my constant bounds, a to b. The moral of the story, biggest picture, it's a big picture, is that you handle the dependency between your inner and outer variables in the inner integral. Does that make sense? It doesn't matter only because you've taken care of how x is related to y in here.
I guess it's kind of weird because that's like in areas like you're multiplying two things. And A to B obviously is a distance, but like I feel like those two feel like a distance when you look at it.
I see what you mean. Remember single variable calc plan for a moment, and remember that this, as a single integral, is the integral from a to b of what?
Of the top line.
I think part of.
Yeah, exactly, or of height as a function of x, right? So this height of x is the result of this integral.
Because 1 dy is the length.
Yeah, length times height, or width times height. There's so many
Yeah, I'm.
ways we can refer to proportions, the dimensions over here. Yes, and so in single variable calc, you would have written this right off the
Oh
cuff
wait.
as x cubed minus 2x
Oh my.
plus 7 minus 3x.
Okay, it's just.
Without hesitation, you've done that. And the moral of the story, which is actually really useful once we get into triple integration and being more abstract about notions of integration, is that you're always integrating the outermost stuff. Okay, the outer integral is an integral of the shadow of the region. So the shadow of this area on the x-axis is what? A to b. You're always integrating over that shadow as your inner integral. But we'll do this more when we get into triple integration as well. There is a problem on a PSET, the very last problem, the last problem. It tells you to deduce what a triple integral might look like for a particular integral. And it basically boils down to saying, oh, my double integral just had my integrand, which is the result of a new inner integral in the third variable.
Now it's out.
What button was that? Oh, was that where we're going? That's funny. All right. What did it say? Is it a mean that we can identify? Okay, other questions? Other questions on double integration? Did that answer the questions? I should ask that too. We had some forward. Okay. How's everyone's throat? How's the freshman play? I see if you were before it gets there. My throat starts to suck.
I'm gonna watch an ad.
Okay. So if there are no more questions, are you sure? Like, guys, you have the power to change the pace of the class. You could like filibuster. I bet I'd be a great filibusterer.
Would you be the guy you're gonna like vilify or the
Yeah, exactly. I'll be Bernie Sanders, right? You got a whole thing for a while. Yes. To go large, 16 ounces, whole milk, hazelnut. Anyone can do a Bernie Sanders impression?
These answers so cool.
Anyone do impressions in general here?
I can do Mickey Mouse.
Oh, okay. Do a Mickey Mouse.
Explain it to integral for us.
Yeah, actually, something Mickey Mouse would never say.
Huh?
Something that Mickey Mouse would never say.
I don't like capitalism.
Yeah, Mickey Mouse would never say that. Those fast passes are making them all that money. All right. That's pretty good. You feel free to chime in anytime with the Mickey Mouse comments about what's going on in the class. I feel like it will be the thermometer for the class. All right. Now we're going to go polar. So bring your, what did I write in the P set? Those Aritzia sweaters, you've seen Aritzia, yes? It's very expensive. They're very noisy. It's awful. The redhead tried to buy one, and we couldn't carry a conversation because it was going, so she returned it. All right. So what are we going to do? We're going to do polar. We're going to go polar. Okay. To go polar, we need to think about what we're doing. Well, normally, two-dimensional, beautiful Cartesian coordinates, we have an x and a y, and we have something that I'm going to try not to draw as a 45-degree angle. Down. Not 45 degrees, just an arbitrary angle, theta. Of course, don't believe what they tell you. And we know that we have a coordinate given by x, y. We're going to go polar. Polar is going to be yellow, because anyone, this is going to be a while, like shot in the dark. If I say the name Frank Zappa, does that mean anything to anybody?
That's one who sings.
Among other things, he's also a famous guitarist, so you're getting it. Who said that? Oh, there you go. Hey, he's got a song. Oh, yes, oh, hi. Yeah, no, I'm not even going to do it. I had to do Beat 'em Up, but you're making it up. And yellow, the yellow snow. Look it up. It's where the huskies pee in the snow. So this polar, because it's cold, right, is going to be yellow, because there's husky pee in the snow. And distance from the origin is called r. This does not mean radius of the circle in all cases. Be careful. Why doesn't it mean radius of the circle? Where can we draw circles? We can draw them centered at the origin, in which case you would be right, R-I-G-H-T. Actually, both senses of the word right are spelled that way, so there's no use to me saying that. But what if we have a circle that is not centered at the origin? Is it safe to say that if the circle's radius is 2, that this circle can be described by the equation r equals 2? Question mark, question mark, question mark? Nope, no way. So watch out, watch out. As Santa Claus would say, he doesn't know, oh, you better watch out. You better not cry. Like that also sounds like something that you'd hear in like a horror film in a minor key. He sees you when you're sleeping. He knows when you're awake. What the hell? All right, so here is r. That is our separation, our distance from the origin. R is always a positive value. And we have theta, or if you're British, theta. Or if you're British and the next word begins with a vowel, theta and z. They throw r's everywhere. Okay, so I learned calculus from a British one. So here's theta, here's r. And I want to write my new coordinates, r and theta, in terms of x and y. So what is y? Whose interphase biography was about trig functions and Taco Bell? Was that you? We're going to look to you for trig advice. Y can be written in terms of what? Yeah, sine theta times what? You got it. And here, x is equal to r cosine theta. All right, Taco Bell. I've been trying to turn off their TVs. Taco Bell that is on Kong Ave. Taco Bell canteen. They got a lot of TVs, and I have my Canon. But I've yet to match the TV code that will make Taco Bell go. I'm trying to find a pun for it. Taco. Go away. Yeah. Oh, yeah. That's pretty good. Okay. So these are our coordinates that we're going to move to. Also, what about theta? What is theta in terms of x and y? Inverse tangent of y over x. Okay, and you're all good with trig? You all mess with trig? Yes, I like mess with them. I'm just say it probably more than is appropriate. Because it's not like when you hammer everything looks like a nail. Okay, so here we are. And all of this to say we're going to go from xy to r theta. That's pretty, sometimes. Some functions are a lot easier to write in terms of polar coordinates than they are in terms of Cartesian coordinates, and that will help us in the world of double integration and beyond. But in order to do that, we need a conversion factor. So my question to you is, when we go polar, are the areas the same? When I have Cartesian coordinates, and I have an area differential, we have discussed how that is dx, dy, and my little piece of area, dA, is dx, dy, or
dy.
Yes.
exactly, all right. Thank you guys, I hope I'm not that much of a pain in the butt. Okay. Where did the Calc battle horn go, by the way? That would have been...
That's a great
Morale
question. I'm so
test.
glad you asked that. I'm glad you're the one asking the question.
That was pretty good. All right. All this to say, we get an area element by taking an infinitesimal step in each of our directions of our variables. We will now do this in polar coordinates. So here I am in polar coordinates. I start at a particular point, and I'm going to have a particular r. Okay. Oh, I should go yellow. Yes. Okay. I should go yellow. Okay. What two variables do I change when I am in Cartesian coordinates, and when I'm in polar coordinates? R and theta, right? So what does changing r by an infinitesimal amount look like?
Going in the line.
Going along the line. So this is going to be dr. Okay? Now what other variable have I got? If initially I'm at some angle, theta,
Oh, you're going.
I'm going a little piece, d theta. Right? D theta. Tiny piece d theta. When I do that, all this, I'm sort of seeking yellow and I can't find it. Here we go. So now I'm going to go d theta. When I go by d theta, what is this going to trace out?
R behind the line.
Ah, yes, we got a little windshield wiper situation, right? We're going by dr over here. If theta is changing by an amount d theta, by how much is this arc going to change? What is the length of this arc? R d theta, right? Remember the arc length, the whole bit, the sector. There's so many words for it. Bonnie, you good? Or you got a question? You good? You feeling better?
Yeah, something like that.
All right. You have a voice at least. I'm glad. I'm gonna lose mine after this class. Huh?
What is an
R plus d. Oh, R. You mean this line? Ah, so in general, if we have this, right? We have a little arc of radius a and angle theta, or let's call the angle alpha. Then this length s is a alpha.
So is that the algorithm
Oh, it is this one.
Oh, okay.
Yeah. Yeah, that's a good point. So this is r d theta. We're making a little change in theta here. D theta. This arc has length r d theta. This arc has length r. So if we do this for David.
No, I was no.
All right. You sure?
Yeah, you're gonna say.
I'm gonna have a comment. Oh, all right. All right. So, but I think this tugs at your question from the other day. This is a tiny enough sweep that we get to say it's basically a little rectangle. What's the area of the rectangle? .com.
.com.
Is what?
R theta. R d theta.
R d theta.
We need to record d theta.
Is it?
Oh, do we?
Oh yeah, actually do. We need.
R d r.
Wait.
Yeah.
What about the 1/2?
1/2.
Normally you would have a 1/2 if you have a single variable calc. Does it cancel here?
We got it.
Because you're like the area of a sector.
There's a 1/2 in the area of the second. Oh, you're thinking like for a circle or something.
Something like. Well,
Yeah.
it applies here. Ish. But then, so is it small enough that you can make it a rectangle? That
Yes.
actually becomes a line.
It is small enough that you can make it a rectangle. That's the bit. I forgot about that 1/2 now. I feel crazy. All right. So what do we have? Do we have our new buttons? Okay. Cool. Thank you. Okay. So this is our area element in polar coordinates. This is our area element in Cartesian coordinates. What's another way to write this, by the way, if not r d theta?
But dx dy.
Yes, and your buttons can't do this because you don't have something else, but what can it be?
R d theta dr.
R d theta dr, yeah. Well, yeah, and although you probably wouldn't do that because you're trying to integrate an r, so I sort of take that back.
So it's dependent on r. It has to stay in that way.
Right. But when we go polar, you'll see cases of how this goes. Okay. Does that make sense? Okay. Let's pick an example, ranging anywhere from very easy to a little more involved. Let me pick something out. We are going to do. Oh, I like this one.
Do you have access to?
Christian dislikes paying for parking. Next sentence. Forgery of quarters is illegal.
I think I was trying.
People sometimes try to use fake coins called slugs to fool coin leaders. And a slug can be modeled by a washer that is the region between the curves x squared plus y squared equals 1 and x squared plus y squared equals 4. So bounded by, so between, okay. The density as a function of xy, the mass per unit area of one of these things, is, x squared plus y squared in grams per unit area.
Density per area. Density per area. That's just.
But yeah, this is density per unit area. Wait, was that the question? Who had the question? Did you have the question?
I
You good?
Just talk about the d-theta part.
Oh, tell me more.
What did I? So it's
No, I was just saying that d-theta is
Some
like
of
your
these are-
change
like
of
these are all
angle.
from this one.
What was that?
Your d-theta was your change of angle.
Yeah, your change of angle, yeah.
Yeah.
What about?
just comments to understand.
I'm just talking about.
Oh, okay. Okay. So we have the region of this, and the question is, find the mass
Wittenberg by Paul.
of the region in the first quadrant. Okay, so what is step 0 for anything? Graph. Origin. Okay, so here we go. What is our region defined by? It's the area between these two what?
Circles.
Okay, radius 1 and radius. And what are we being asked to find? The mass of this shape, but where?
Between the two.
In the two in the
First quadrant.
first quadrant. So what is our region that we're going to integrate?
From y x equals square root 10. Well, x equals that circle. It's x equals that circle. Y equals that circle.
Right, but in the first quadrant, right?
Yeah.
So here. So we're going to shade in our region R of integration. You usually denote that as R, capital R, our region of integration. Okay, what's the next step? So step 0 is draw. What's step 1? Step 1 is going to be to pick an order of integration. And this one kind of gets fun after because no matter what you pick, you might make different choices shortly. But humor me. Pick an order of integration.
Let's go dx dy.
Okay. So figure out.
He wants us to see how bad it is.
That's exactly it. Yeah, we're going to build character one last time, and then we're going to go polar because we can now. Okay. So what order of integration do you guys want to do? Does it suck either way?
Yeah.
It sucks really, really badly. But give me one.
Let's go dy dx.
Let's go what?
dy dx.
Okay. dy dx. So we're going to go dy dx. Very nice. Okay. Step 2. Figure out the bounds. Notice that none of the initial steps have anything to do with the integrand, right? So what are we not worrying? We're not worrying about mass, we're not worrying about density. What is all of this attention directed toward right now? Area meaning the bounds, the region of integration. We don't know what we're going to multiply that region's little pieces by. We just want to make sure we define our region. Okay, So dy dx. Okay, so what are the bounds on y?
How are we gonna get the mass for 3?
What do we multiply to get mass if we have mass per unit area? But let's pretend it's two-dimensional. Like, let's pretend that it doesn't have a third dimension.
Dimensions, grams per unit area. How do we just get grams? We multiply.
But I think he has it. You understand that bit, right?
Yeah.
You're saying how do we get it if it's a real object, if it's 3D?
But it's
Yeah.
not that. 2D flat line.
Right, we're treating it as 2D flat, right? Yeah.
2D grand.
2D grams, yeah. We'll go up to 3D in a moment, but it'll be right. Okay,
But it's time to be.
beautiful. So what are the bounds on y? We're going to enter the region at y equals. Are we though? Remember, this is our region. Y equals 1? Is it always y equals 1?
Oh! X equals square.
Y is equal to square root of 1 minus x squared. And we're going to come out at square root of 4 minus x squared. This way that 1 and 4 sound muffled makes a critical difference when you're spotting somebody or working out. When I was a freshman, I was spotting my friend Michael at the gym. He was benching and he's struggling hard. And he goes, 1 more. And I heard 4 more. And I was surprised because he was struggling. I'm like, oh. And so I'm just like, huh. And I just like verbatim when I said, 4 more. Well, if you insist. He starts to laugh. He can't even finish that one. I screwed him up big time. There was another time, IP 2016, I was the SPA. I was on the elevator at Massey where there was some air conditioning. And we're in the elevator, and I go in and I press a number, and then someone else comes in, they press another number. Before I know it, like almost all the numbers on the elevator are pressed. And I'm on the 6th floor, so I gotta wait for all these people. One more guy comes in. He looks at the elevator panel, and he says, this. And I thought, wow, he's speaking to what's in my mind. And then I hear someone press the number 4 for him, and I realize he said 4, please. All right, I lost it. Okay, so we're going from 1 minus.
Minus x squared to 4 minus x squared.
What he said, okay. 4 minus x squared to root 4 minus x squared. And the bounds on x are going to be what?
0.
Yeah, ooh.
Oh, 0 to the end of the circle.
Easy there. So is this are we always entering and exiting throughout the entirety of the region? Something goes wrong, yeah? Where?
End of the circle.
Oh, at the end of this circle. I think meant at the end of this circle.
Whoa, I just said.
Yeah, why would I suspect you of thinking that? You're right. All right. So x goes from 0 to what? To 1. Yeah, exactly. Sorry, no, I don't know why I was so skeptical. Yeah, I know, it sucks. All right. So we actually need 2 integrals. This is area number 1. And for area number 2, what are our bounds going to be? Y enters at? Oh, I said it down. All right. And Noah, where do we come out?
Square root 4 minus x squared.
You got it.
Can Mickey
Okay.
Mouse say it next time?
Mickey Mouse can say it next time if he pleases. Okay. What? Did someone say my name? Okay. So this is going to be for area number 1. And then for area number 2, our bounds are going to be y goes from 0 to square root of 4 minus x squared. And x goes from what? 1 to 2, right? Okay. Step 3, I think we're ready. Set up integral with integrand. What's that? Double integral. What goes here? dy dx. What is our integrand if we are trying to find mass? Density as a function of x, y over this region of R. Okay. One way to think of density is it is m by dA, amount of mass per piece of area, right? How do we think of dy dx? What is dy dx? dA. Does it make sense that we would then end up adding a bunch of tiny masses and getting the total mass? Yeah, that's the bit with density. And in 3D would be dm by dv, d volume. And then that would be dx, dy, dz, or some crazy amount of variables. Oh, is that? We more buttons, yeah, I gotta get with it. All right, so step 4. Solve. Oh, we need to put our bounds in there too. So we're going to solve integral from, we actually need 2 of them. So we need, my God, this is going to be fun. What do we have? X squared plus y squared, dy dx from 1 x squared is 4 minus x squared, 0 to 1, plus integral from 1 to 2, 0 to square root of 4 minus x squared. What do we have? X squared plus y squared, dy dx. Okay, how do I convince you that this is so annoying?
Not a lot.
What was that? Not a line? What is it? What is it? So someone said something.
No.
Oh, I was just saying you might want to multiply. If you're doing it for extra, you can do less than that.
Say again. Oh yeah, we're only doing the first quadrant.
Oh, okay.
Yeah, that's the bit. All right. Yeah, that's a really good point. Okay. Oh. Lila, I met someone who went to your middle school and high school. Her name is Sora.
Sure.
Yeah. She was my Calc student last semester. So, funny how all the Brookline people end up here. That's really cool. Okay, so now here we are. Let's do this a better way. What do you want to do? Go polar. Please go polar.
No.
See, you guys want to do this? All right. Yeah, the threat is real. 0, 1, 1 to 2. Okay. If we reevaluate this and we go polar, let's go right back to it. We know that our mass is equal to our double integral of our density in xy, dy dx over our region R. Let's plug it in. This is x squared plus y squared, dy dx over our region R. But now, let's end the suffering. What do you want to do? You want to go polar? What about this makes you want to go polar? A few hints.
I see circle, I see
You
circle.
see circle, and what else do you see?
I see.
X squared plus y squared, right? That's like, what's that? Distance from the origin squared, that's called r squared. Beautiful. So we might as well go polar. So if we do that, what does this become? Let me go yellow. This becomes r squared. What does dy dx become? Yes, okay. And what do our bounds become? So far we have r squared, r dr d theta. What are the bounds in R if you're going from one circle's edge to the other? 1 to 2, right? And the bounds in theta? Oh, hey. Oh,
This isn't the printer, but it looks like you have your notes.
that's wonderful. Yeah, I need it now.
Cool, yeah, got you covered. Yeah, lecture notes, you know.
Yeah. Good stuff. Oh, wow. Woo. Bye-bye, Ken. Okay. So, okay. So what are bounds on theta?
0 to pi over 2.
0 to pi over 2. Brilliant. Yeah. And it's not 0 to 2 pi because we said the first quadrant.
But Christian, I
Yes.
have to ask one question.
Yes.
We're getting all that graphically, like our bounds graphically. Is there a way we can get them just off of our bounds themselves?
Oh, if I give you bounds, can you draw the graph you said?
Oh no, like if I only had my bounds of like y and x, how can I use those bounds to algebraically find mine?
Oh, you bet.
Could we-
My intermediate step would be drawing, but sure. Well, let's see.
That might be an after lecture question.
So y is going to go from this to this. What does that look like if you solve, like if you write it in polar
Y is
way?
equal to
You write it looks like x squared plus y squared is equal to
4.
4, and x squared plus y squared is equal to,
1.
and then you're like, ooh, that's 2 circles. And then you go polar.
R. Oh. E.
Yeah. Hi.
Interestingly, the inner bounds are in terms of R and the outer bounds in terms of theta. When you're doing like this, the inner is in terms of like outer bounds.
Yeah, because how are we get data off of those then? Because we really can't get data off of these.
What do you mean? Oh, you're saying you want to write stuff in terms of theta?
No, I mean like, because doing that gives us our bounds for R, we just did just now. But how can we do that for data?
Oh, yeah, I feel like I would try it at that part though.
Really, there's no a workshop problem. One single workshop problem for your other class.
Really?
The Catalan constant or
The
Catalan.
Cadillac?
Yeah, number 6. That's an acronym.
Okay, let's talk about it after. I'm sure there's a thing, but like that's kind of more of a crazy joke. All right, so this becomes the integral of r cubed dr d theta 1 to 2 0 to pi over 2. Do we trust ourselves to solve this?
Yes.
Okay, you want to do it anyway? No, we good? No pressure. Let's do it. All right, I like it. I like the city. Let's do it. Okay. What are we going to do? So, what is our convention when we do double integration? First, we start with our inner. Right? What is our inner variable of integration? It's dr, and we have an integral from 1 to 2 of r cubed dr. What is this? What is the integral from?
R4 to
1/4 r4.
2
R goes from 1 to 2, yeah, to 1,
Looking like 15 over 4.
Wow, you're quick. Yeah, I believe yes. Oh, because it's what? 1/4, 2 to the 4th is 16.
Minus 1.
No, you're quicker with algebra.
Good job, Bill.
Oh, right, 15 over 4. Cool, congrats. Oh, we're not done. Sorry, what's missing?
We need to put the integral in the outer and the inner.
Yeah, so now the outer is from 0 to pi over 2 of what? Of inner. Theta. And actually, the inner has nothing to do with theta anyway, so what's this going to be? 15 over 4 times pi over 2. Yeah? Yeah, okay. A little bit of a delay there, but we're okay. 15 pi over 8. Does that make sense? Okay, cool. So that means, yeah. Oh, I wrote something here, which was, so now that you know this, it means that you can write this. It means that this whole thing, you know that this whole thing evaluates to what? 15 pi over 8. Which means that on someone's 15th birthday, you can draw on it 8 over pi this, and that's the birthday cake. And then they're gonna look at you like, what would Mickey Mouse say in disappointment?
Nice video impression. What?
Okay, so are we good? We got, yeah, hi. I did it.
If you were to evaluate that,
Mhm.
Cartesian, how would you get a pi at the answer?
The trick sum.
Trick sum.
Because you have to do the trick sum for the 4 minus x squared.
What?
Because the 4 minus x squared, if you do it inside, it'll be, like x squared, x squared. If you sub it works, you have to do trick sum. And that trick sum gives you the pi somewhere. You don't.
You don't, and I won't ask you
That's
to trick
the
sum.
point.
I don't trick sum.
That's how Sammy sum.
Yeah, evil Calc Sammy. So what do we got? Why is it evil?
Because he uses trick sum. That's.
Just like three.
I learned these days Yeah.
No, you.
Can you pull out the other board?
Yeah, yes, you did.
What do so you know you have like the little.
The little DA, yeah.
What about the area of your?
The area under this?
No, like so like the R area.
Oh, because there's like.
Wait, what?
Technically, it's technically a bigger windshield like this.
There's a slice on top and a slice on bottom.
You mean like this piece?
Yeah.
Oh, we're looking at the change in area. So the original area, okay, so if we had a particular theta, right, okay, so let's do this. If we had a particular theta, right, at a particular r, its original area is this, right? We're looking at the change in area, so the dA. By how much does this area increase when I do a little sweep this way and I stretch out that way?
So how do you get a full like the area of the circle from that?
And now we get the inner.
Yeah, with the inner wedge, like a slot.
How do we find that?
I'm not following, but I think it's a me thing, so keep, what do you mean?
Why is it not like the entire wedge from the point user? Like, why is it not a triangle shape? Why is it a rectangle shape?
Oh, because we're making infinitesimal changes. So we're tiny enough that we can approximate it as a square. You know, like small angle approximation, like sine of theta is approximating theta. Tiny change this way. Think about it, if you're walking on the earth right now, right, we're curved. You're taking a step on something so big, an infinitesimal step, it feels flat. Does that help?
So what if,
Wait, but we're talking about the other.
like, what if R is constant then?
Come dry. I'm not saying this, but I'm sure we'll get to it.
Like, it's just like a double integral, so you go go all the way down to dr.
So like,
So you're doing
if we want this A, how
Yeah.
do we like, and you said that there's this other like, you know,
Yeah, that extra piece that we get when we
dr
get.
RD theta, how do we get this area right here if we're doing this, like if R doesn't change, if there's really no dr, R is constant, how does this apply?
Oh, well,
Is that what you're asking?
oh!
Do you-
Is that what you're saying? So if you hold the radius constant, you just.
Yeah,
Yeah.
yeah.
Oh, okay. So I'm gonna draw that bigger because I think I'm seeing it.
Is that what-
Okay, so you're saying if we have.
I mean, this is also
Something like this. This is R,
Just do the first.
this is theta, so this is, and we're trying to find, and we have the area of this. And then you're saying if we sweep only in the theta direction or only in the R
Only in
direction?
this space, like R is constant, R is constant.
Okay, so we sweep, so we increase theta by a little amount. D theta, you're saying. Well then, what do we have? We have this, right?
This little argument.
This little arc length, yeah, d theta. Oh, but for that, hang on, wouldn't that be, that little piece is d theta, that radius is r, this is r d theta.
So how do we use that to find the area of a circle? Because I feel like, because then wouldn't we use that for this? Because that's a circle. Oh.
Well, it's just, you're doing two integrals, so you're kind of, the first step is, the first interval is what you're talking about, and then you go around.
So what if we were just doing a single circle then? Like a full
I
circle?
mean, listen, so we sweep this all around, you're saying if we sweep this all around,
Yeah.
what's this? This is the integral of,
0 to.
oh, but your radius is constant, you're saying, right?
Yeah.
Okay, so what's your radius? Let's, instead of calling it little r, let's call it big R.
Big R.
Okay.
So we're going from 0 to pi.
R d theta. Sorry. Wait. No, yeah, exactly.
Wait, we can make that into a double integral. We start
Yeah,
with
okay. That's exactly what we should do. 0 to 2 pi, what goes in here?
0,
0 to r,
R.
okay, r dr d theta. What do we get from that?
Why is it still R d theta?
Because that's dA.
That's true.
Wait, what is DA like on the diagram?
You're saying by how much this, like, what is this piece of area?
Is that DA?
This little piece of area? That's, what's that? That's
R d theta.
r d theta times r. Right? If it's tiny enough to be like a rectangle,
Oh.
Oh, it's like a little.
then it's this length is r d theta, this length we know is r, length times width, yeah? None of this is supposed to be obvious. This is actually a cool way to go about it. So what do you get? You get r squared d theta. Oh,
Oh, and then that's it. I see it
Yeah.
now. Because the area of a circle is, you just should do it.
yeah. Oh, now I'm tripping up on arc length stuff, but I guess there should be a 1/2 somewhere here.
No, because of the 2 pi, the 1/2 makes you pi r squared. It is the area of a circle.
It is the area of a circle, yeah. But where's the 1/2 coming from?
No,
Because
you're
you-
integral.
Because when you anti-derivative.
Oh, yeah, that's 1/2 r squared, and that goes to pi. Yeah, absolutely, okay. Well, that was fun. All right.
Hey, at least now we know.
Yeah, that's good stuff. All right, questions? I've never dissected it this way, but it's fun stuff. All right, questions? Oh, hi, Vaughn.
Hello, okay, so when we have like x squared plus y squared dy dx, how do we determine that that's r squared?
Because in polar coordinates, distance from the origin is x squared plus y squared. Sorry, distance from the origin squared is x squared plus y squared. Right? Distance from, right, r, oh yeah, I see what you mean. So, in polar coordinates, we have y and x in terms of r and theta. What is r in terms of x and y? It's square root of x squared plus y squared, right? Because it's this is the length of the triangle, the length of the hypotenuse. Okay, more questions?
What if it's not on the origin?
What if it's not centered at the origin?
Yeah.
Then, for example, if it is for a circle that's not centered at, well, okay, so 2 things. R doesn't refer to radius of circle, it refers to distance from the origin. We're working on that. R is distance from the origin always. So if you have a circle centered at the origin, its R is always constant. But if you have a circle that is not centered at the origin, or really anywhere, then its distance from the origin is not always the same. And we just need to find ways to express that. Make sense?
Because now it's not 0 to r, it's 0 to the function of r.
It's 0 to the function of r, exactly. Or the function of theta. Okay, more questions? Okay.
ways we can do substitutions?
Yes,
Is that where?
excellent segue. All right, well, we're all good with polar, we're all good with any questions for polar? Okay, we are now going to go to a whole new set of coordinates that you get to choose. And to motivate this, I'm going to pull up a little applet. Okay, this next part is called going to a happy place. We're asked to integrate over a region that in xy space is a very ugly blob. We want to write our integral not in terms of dy dx or dx dy, but in terms of some new coordinates. This is u substitution expanded to 2 dimensions, and in this beautiful, beautiful new coordinate system, uv, our new region, which we will call r twiddle, a relic of learning calculus from a British woman, is the twiddle.
Edit? We gotta be Hispanic here. Edit.
What?
No.
Our edit?
Edit.
Oh, like Reddit?
Edit now?
No. This is almost like a happy. Alright.
It's another.
Yeah, R enya, yeah, like an enya, yeah.
Edit. Edit. Edit.
As in, yo, que clase de dificultad. Double R?
Oh, edit is a double. Oh, wait. Oh. No.
Wait, who
No,
can
I
roll their
don't
R's?
know Espanol. Okay. Edit.
All right.
That's it. Sorry.
Alright, cool. So we're going to go from dx dy to du dv. Okay, in a very, very general sense. This is called the change of coordinates. I'm going to pull up my map, and we're going to look at some stuff real quick. Laptop presentation, hide image, show.
How can I get it? For the circle? The area of the circle, the reason I still argue on the data, because instead of going from one circle to another, I want a circle that has 0 radius, it's the next one. It's still technically 2 circles.
I don't,
Why did I wish you wanted to for that and why does it not work? For this, no. Here.
I get the sense when this pattern is
Oh,
one where you
oh,
you're just gonna have to
sorry,
have like
stonks.
words and all.
Yeah, it's the meme stonks instead of stocks.
But
All right. So let's open a new window.
Yes, I
Okay, here's a change of coordinates. We are going to just make it going polar for now. Let's see if this works. Python, nonlinear transformation. Okay. Left is Cartesian coordinates, right is polar coordinates. And the question becomes, what have we done? Something that's really fun to do is, can someone draw a grid really quick on their whiteboard and bring it up? I guess we're seeing it with this, but it's kind of cool to see it. You want to come up now?
no, yeah.
You sure we could do your faces? Or is it
No,
also-
no.
So here we are, and again, we're going from Cartesian to polar. And you notice it's a spiral unless things are perfectly centered, which is kind of cool in a way to think about spirals. Okay, what else can we look at in this polar distortion? And the circle's another circle. We center it at the origin. That's a good background. I can also go from polar to Cartesian, go the other way, but we're gonna keep it here. Okay, now what I'm gonna propose is that we not go just polar, but we pick a much wackier set of coordinates. So, what do you want u and v to be in terms of x and y? If u is x and v is y, what are we gonna get?
The same thing.
The same thing.
If you move it, oh, it's like transformations all over again.
It is like transformations all over again. Did someone say matrices? All right. What if u was 2x?
big V, like X, Y.
Big V, be xy. So v is xy. Is this, you wanna do this?
Yeah.
Okay, let's see what happens. Let's see what you do to my face. What have you done?
Oh, that's weird.
Actually, but actually, so what do you expect for x, y? What kind of behavior are we gonna see?
X.
When x and y, when x or y gets bigger.
Yeah, and actually, I'm treating the origin as the center of this,
Oh,
that's
when
why.
x and y are negative, it flips and becomes positive.
Yeah, that's why my ear is pointing up here. Right, and yeah, and you see what the axes do. All right, let's pick another. What other change do we make?
Y over X.
Okay, so 2x and just make v equal to y. I like that.
Y over
Y over x.
Y over x.
We need to torture, I mean,
Yeah,
well,
we're
we need to
stretching.
condense this question a little more.
All right. What's that supposed
That
to
means
mean?
when x is zero.
Y over x.
So what's gonna happen when x is zero?
Oh, that is good. Oh, that's.
Whoa, wow. I'm a singularity. But I'm coming out the other end. Wow, okay. That's pretty cool.
But because x is negative on that axis, you're flipping yourself.
That's pretty cool. All right. What else we got?
X cubed.
X cubed. Okay, and then v is y over x or something else?
X was what?
X plus y. Okay, let's see. Oh, it's back rooms. Oh my god.
That's the calculator.
Wow, that's freaky. I've done this before, but never at an angle before. What do you think would change if we make it, if we change these slopes, maybe 2x plus y?
You go at a bigger secret angle.
Yep. I want to try that. Oh, 2 times x, yeah, sorry. Okay. That's pretty cool. All right, and lastly, we'll just make it v equals y, so we can
Do
see.
x to the y.
Yes, we can. Oh, now you sound like maybe my crazy website when I was in high school. What's it doing to the stuff on the board? Whoa. Yeah, what's that dA? And actually, that's going to be our next question. X to the y? Wow.
Should I draw out a dA for you just in case? Can you prepare one?
Sure.
Okay.
The draw, okay.
Move it into dy, move it into dx.
All kinds of, wow. I've been told I had a big head. I said that on the top, it's only because, wow, that's rough.
Oh my
You had a 5 head, a 6 head, whatever exponential, I got an exponential head. Okay. Okay, beautiful. I'll take one more, actually, we're gonna go, you're gonna do it? You're gonna give us a dA?
Here's your dA.
Okay, I'm gonna pick, yeah, let's do this one now. Here's dA. But it's weird because it's gonna get, yeah.
It starts to
Yeah, stuff gets right. So what's your guess? When the area gets into this new coordinate system, is a piece of area bigger here or in the original coordinate space?
It depends on a scaling factor.
It depends on the scaling factor. Ooh, I miss it. But would you guess that the scaling factor is greater or less than 1? Greater than 1. It's getting stretched all kinds of crazy ways, right? And in fact, that is what we will explore. So I'm going to pick a slightly less radical choice here. I like this x cubed x plus y situation. And if we do this, again, this is our coordinate system. I want to change a dA here to a dA here. And what is that scaling factor? I can also see that as this yellow square here. What is its area under coordinate transformation? And that is going to lead us to a conversation about change of variables. So let's do that. But does everybody see the point of this? And the idea is that when we go into this new coordinate space, stuff gets a lot cleaner. Okay. So to do that, let's erase it. Fundamentally, like Noah said, what do we need when we're going from one coordinate space to the other? A scaling factor.
Jacobian.
Oh my God, Jacobian?
Jacobian.
All right, Mickey Mouse, I guess we have to do Jacobian.
Oh, Hessian.
If you were to push where it makes that
Mickey Mouse Jacobian. Oh, Hessian.
Oh, because it's got ears, right?
No.
This looks like orbitals, though, right? Or something.
Those are their orders.
Or like lone pair. I've been spending too much time. All right. So, but yes, we're no Hessian yet. Hang tight. Okay. I want to remind us of what the heck the Jacobian was in the first place. The Jacobian, if we have x, y, and we're going to a new set of variables, uv, what was the Jacobian?
dx dy.
Yes, du by dx, du by dy, dv by dx, dv by dy. Ooh, okay. Now, I'm going to start in xy land, which I'm going to call this, and I'm going to go to uv land. In xy space, my little piece of area is given by dx times dy, right? One way to see this is the result of a parallelogram from two vectors. The first vector is a tiny change in the x direction. What does that look like? What would this look like as a vector?
dx0.
dx, 0, tiny change in x direction, no change in y direction. And then dy, what would the dy vector be? 0 dy. And our dA is the result of finding the cross product, which in 2D boils down to being the determinant of the matrix given by dx dy. That is to say, the determinant of dx 0, 0 dy, which is what? What's the determinant of such a matrix? What's the area of this parallelogram that's actually really nicely the square? dx dy. Okay. Now, we're going to do something. We are going to change our coordinates. And the way we're going to do that is with the Jacobian. So I'm going to take my initial dy and dx arrows, our vectors over here, dy and dx. And I'm going to transform them by this Jacobian. What Jacobian is this, by the way? What's the subscript over here?
X, Y, U, V.
Or no, uv to xy, right? Because think partial with respect to x and y. Yeah? Everyone good? Not so. This will be okay. Okay, so let's first transform dx by the Jacobian. What is j times dx 0? It's this matrix, du dx, du dy, dv dx, dv dy, multiplied by dx 0. Okay, 2 by 2 matrix multiplied by a vector, 2 by 1, gives us a 2 by 1 vector, yeah?
Single column.
Single column. What's the first element of that column? How do we do this? Row picture, column picture, what do you want to do? What's easier for this, actually?
I like the.
You like the rows? So du dx plus 0 du dy plus, and then on the second element, dv dx plus 0 dv dy. I think for this one I like the column picture more. I didn't know this before now. Who said column picture? Leanne, did you suggest? Or Lily, you suggested? What's the column picture? Oh, you got the thing. Yeah, du dx and not plus though, remember, because they're different elements.
Oh.
Yeah, but you got it. So this is du dx dv dx. Okay. So that's dx transformed by the Jacobian. Now, does it only have x components anymore? It's got 2 components, right? So think of it as taking this and like distorting it a little bit. Does that make sense?
Mm-hmm.
This is our new dx. We're going to call it dx prime.
And matrix language, why do we do this in the first place?
In matrix, we're doing it to transform our differentials.
Oh, transforming it by our Jacobian, okay.
Yeah.
Yes.
Yeah, okay, beautiful. What if we do the same for dy? Anyone want to lecture theory what this would be? If we apply the Jacobian to the differential in y, pattern recognition can serve as well. We could also multiply the matrices out. It's going to be du, dy, dy, and then, yeah, the next one, dv by dy. Okay. So these are our new bases in our new coordinate system. Everybody good so far? Now what I want to do is figure out what a piece of area in this new coordinate system looks like. So how do I find the area in this new coordinate system if it's going to be spanned by these two vectors? across them, right? We're going to find the area of the parallelogram that comes from these transformed coordinates. And if we do that, here, here. So this is what we're looking for. This is going to be, let's say, dA prime. And what is that going to be? It's going to be cross product, which if we work it out, what are we going to get in the end? We can do the multiplication. It's going to be the determinants of what matrix? Yeah, let's do that. The determinants of what matrix? Where's it going to come from? Yes, so these two. So dx prime, dy prime, yes. And then we're going to do that. I'm going to do dx prime, dy prime.
Because there's a,
So it's going to be du dx dx, dv dx dx, du dy dy, dv dy dy. And if you do this determinant out, you're going to get that this whole thing is du dx dv dy dx dy, right? I'm just grouping stuff. Plus or minus du dy dv dx dx dy. Okay, why the heck does this matter? This is our area. This is our area in these new coordinate systems. And what do you notice about it? If we factor out dx dy, what is in here? Du by dx, dv by dy, minus dv by dx, du by dy. I just changed the order of these, but same idea. What is dx dy times something? What is this something? Who said that?
Is that the determinant Jacobian?
Yes, it is. This is the determinant of the Jacobian that goes from uv to xy. That is the meaning of our scaling factor. Yeah, David.
So if we're going from xy to uv, would you just put the Jacobian on the other side?
Exactly. Well, but a different Jacobian though.
Yeah.
so
Yeah,
there's
yeah.
a proportion of like the Jacobian.
At which part? Yeah, absolutely. Oh, actually, I'm gonna go into more about it than just clarifying. So I'm glad you're saying that. Give me 1 second. Okay. So what this is saying is that our new area, which is in terms of which coordinates again? U and v. So this is du dv. Yeah. Du dv, which is our new piece of area, is equal to this. That means du dv is equal to determinants of Jacobian uv to xy dx dy. Another way to see this, what's another way to write the Jacobian? What's our other notation for it? In like the derivative way. Yeah? duv, beautiful, by dxy. And here you can abuse your notation as you wish, because what's going to cancel? Cancel. dx dy, and you end up with du dv. So, to end up in uv space, you multiply your area in xy, or your differential in xy, by absolute value of the Jacobian. But a very crucial point emerges, which Loianne and David were pointing to, which is usually, when I want to solve an integral, what's my whole objective of changing coordinates? Do I want to end up with a du dv or a dx dy? I want to be integrating du dv, right? So what do I really want to do? What do I really want to do? Yeah, what I want to do is I want to have something on this side. Does that make sense?
So we have to move it around to get dx dy.
Exactly, and this is where a very important aspect of
Oh, and like single variable land, it's like using.
yes, yeah, of course.
Wait, what is some
Okay, tell me. So where? Here?
You were like, it's like the other side.
Oh, absolutely. So when you do an integral, right? We're trying to go from doing dx dy to doing something du dv, right? But right now, what we have unlocked is a relationship that says that the integral of something dx dy gives me du dv, right? But if I do an integration right now, I'm still going to be integrating dx dy. What I want to actually have in my integrand is the my integral is the du dv, right? So I basically want to move this to the other side of the equation. So, what do we have? We have the following. Dx dy, this is like u substitution in what way? Yeah, you were going to say. That was one.
Oh, wait, what? No. This is U substitution where, wait, what was I getting?
I don't know, you would get like a 1 over or something.
Oh, I was gonna, with 1 over the scaling factor.
1 over the scaling factor. Dx dy is 1 over the determinant of the Jacobian from uv to xy.
Oh, it's like
Du.
we use sub in single variable land, and we have to go back and forth to kind of solve for our.
Okay. So this is how we will do our u substitution, or uv substitution in multivariable top. You pick your new coordinates, you find the Jacobian that takes you, that does duv by dxy, and your scaling factor is 1 over the determinant of that Jacobian. One very useful property of determinants that may come up, but probably not frequently, is the following. Actually, let me get the slides up because I won't leave that. What do you got? Alright, oh, this is actually perfect timing. A matrix is a transformation, yes? So if I have a matrix that stretches a square by a factor of 2, by how much does this area change? By 2. The inverse of that, so what is the determinant of that matrix? 2, it's the area scaling factor. What do you think the determinant of the inverse of that matrix is, knowing that that matrix inverse takes you from 2 to 1? 1/2. So that gives us the fundamental relationship that the determinant of the inverse of a matrix is 1 over the determinant of the matrix. And, said another way, the determinant of a matrix is also 1 over the determinant of the inverse of a matrix. Usually, we're going to write u and v in terms of x and y. But if for whatever reason we wanted to write x and y in terms of u and v, then we would have a different Jacobian. It wouldn't be uv to xy, what would it be? Xy to uv. And so if we find the determinant of that one, if we find the determinant of xy to uv, this whole term becomes, yes, it's the one for xy to uv. Jxy to uv. So this, another way to write this is determinant of Jacobian from xy to uv du dv. This comes from the fact that, this comes from the fact that what is the case? Yeah, because 1 over the determinant of this is the same thing as the determinant of the inverse of this. The inverse is the reverse transformation. Okay. So when you do these u substitution problems, what we're doing is we are finding the Jacobian and drawing the whole u sub, change the variables and all that. But this is the mechanics by which that's done. Okay. Questions? Okay. We are out of time, but please hang out. We'll keep doing stuff. All right, you guys. Oh yeah, which one this is? Oh my God!
Talking about last night.
never trust my friend again. He was like, "You want to make a bout He took me to the depths and made me see the guy that was crushing. In my head, broke my head. That game has so many like
Lower university. What is determined for that? I think it's like you manage to like where we're right now. I don't remember exactly what I had. But I feel like if I was teaching this, it would have come to me, I think it would have kind of. That's it. Feels a little bit like a Oh, yeah. Yeah, I'll see. Yeah, it's not, I guess it's a vision, I don't like shit. But this is the same that I made, the vector is a multiple of another vector. Oh! In my mind, this is not nice.
My name is John.
That makes sense. Yeah, so this is just a system of equations. And you know that this system of
Very well.
has
I'm still not better. What was your ask? I think it is. I hope it is.
yeah.
Like everything.
Oh, I didn't know. So this part makes sense for it being a singular system because it means that the determinant is 0. Right? Because that makes sense. We're trying to solve for this, right? And it has a non-trivial null space. That means that x, y is x, y. And the only way that that's the case is what? Yeah, so it's not full rank. Meaning it is not rank and it has a determinant, meaning it's singular. That's what it is. But do you see that now?
Thank you, Christian.
Yeah, of course. See? And that makes sense. So if they're parallel, then that makes sense. Yeah. Okay. Well, that was really cool.
So saying that everything is going in here.
Let's do it. Once I'm written down.
During that 5-minute break, I fell asleep and I wake 2 words completely filled.
Actually, I'll be waiting on you.
I think it was in the fourth class. Yeah.
Oh yeah, did you do it by your own?
Yes.
Oh no, Louis. You gotta keep. I think I have a call. Okay, yeah, let's do it. So the first problem I wrote was prove the conversion factor from Cartesian to polar.
Well, I can say.
But yeah, we don't want to prove. I'm with, let's just do it. Find the area in the first quadrant of this tree.
Like a bounce? Or you mean
Let's use this.
Oh, right.
I mean, you're probably, if you want to use the iPad, that's fine.
No, that's just the function you gave us for the last one. And
Or no, it's not.
what? Not in the beginning.
Oh, it's not really the,
Oh, yeah, it is. Oh, it
the
is?
height is not the integral, the inner.
Yeah.
So
Oh.
why is it inner part? I guess the better.
But this one is kind of wacky looking, so accept my drawing it.
Oh.
But the point being that this is really ugly, right? Imagine integrating this dy dx and dx dy. Yeah, yeah.
It's not just one number now, but it's
Oh,
it's
look
minus
at
that.
it.
So
Yeah.
that's an apple question.
Oh, it's probably, it's not, this minus the
Oh,
x.
yeah, probably.
This top part minus that part will always give you that height. Or not the height, the length.
It is, it is.
The distance.
Sorry, and these are the curves.
Yeah.
X,
So I don't-
X,
I guess
Y
I-
equals
But
3x.
the other solution is that one.
But
I
now
don't
this
understand.
Why would you do it here?
Okay, beautiful.
And then
Okay.
dy dx.
So you're trying to find this. Now, this is really ugly in Cartesian, but you might want to go change your coordinates. So what would that look like?
So, the height is associated.
The height is here.
Yeah, so then let's pick our new variable. So u is equal to,
And then, it's just, oh, it's, we change it somewhere.
you do whatever you want, but think about what's convenient, think about what makes the bounds pretty. xy equals 2 to xy equals 4.
Or we're talking about the
xy cubed equals 2 to xy cubed equals
From
8.
1 to 2, from this part to this.
That makes sense
So
to
from
me.
the beginning of the circle, it's a height there.
Okay,
Yeah.
so what are the bounds in u would be?
Is there a reason why,
draw that
like, why
in
would that just be right here?
Oh.
Why do you have to have this?
Oh, no, you don't, you don't. That was only because of our question, our specific question.
Yeah, but I mean, in this case.
In this case,
So it looks easier. The only price you pay for the train easier region is you need to find the conversion factor.
This is mass.
So let's do that.
Mass per area. So we got the mass per area times our area. But if we just wanted the area of this curve, it would have charged.
Mhm.
It's a unit string. Can you explain it this better, like why we have that square line?
I mean,
And
yeah,
then
it's just because the question was asking, is what is equations unit area, right?
What is the y here? Oh, y, yeah, yeah, yeah. I heard you say y.
So